Assalamu alaikum everyone. Welcome to today's video of numerical methods course, where we will first talk about numerical value representation. So let us get started. In this slide we will have a total of 5 topics, which is the number system, number conversion, representation of numbers, computer arithmetic, and errors in arithmetic. These 5 topics will be covered, among which in this class we will cover number system and number conversion, and if possible a little bit part of representation of numbers. Let me add as well that most of these topics that we are going to discuss are actually somewhat you should know about them from your previous classes or during your previous courses, or even from your before university classes or so these topics are a little easy, but I will try to induce the algorithm leveling or a programmable systemization, so it might be easier for you to understand how we are going to proceed with the rest part of the course. So let us get started with the number system. And number system are actually of initially they are called of two types: non-positional number system and positional number system. Non-positional number system, as it is said, it means it does not care about the position of the number. For example, we can say the Roman numbering system. If you remember the Roman numbering system, it is written as like 1, and this is like 2, and as you can see, the position of the number does not matter. Even in Roman numericals, this is something like this is usually interpreted as, I think it should be 30, this is 39. So regardless of the position x is in, this x value is in, it always represents the number 10. But in positional number system, the difference is that we do care about where the number is. For example, in 1 it actually means 1, but in 2, 1, 5 the actual value of this 1 is 10. Confusing? If it is confusing, consider it like this: the 2 over here is actually 200, the 1 over here is 10, and the 5 over here is 5. So when we sum them all up, we get 215. Actually, this is the concept that is used in positional number systems throughout. This is actually the how positional number systems actually work out, which is not the case for when you're using non-positional number system. For example, the Roman numbering system. When it comes to positional number systems, we will be discussing about decimal, binary, and hexadecimal. In computer science, once there was a very use of octal number systems as well, but I will skip it for this course as it is not being used much these days. Decimal is basically used because historically, as we have heard that decimal number systems are working because our fingers, in total we have 10 fingers in our hands, so it helps us to learn counting. We will learn a little about binary number system because computers essentially always work with binary numbers, so we will learn a little about binary numbers. And so hexadecimal numbers itself is not exactly used in computers, but for various reasons in various courses we do use hexadecimal numbering system. And why so? There are some applications of it to express some facts in computers, so we will talk a little about hexadecimal number because it is essentially important to us. So that is all for that part, number systems. What we really want to talk about today is number conversion and how we can convert numbers given in a say decimal or a fixed system into another. So let us start by understanding how to convert a decimal number to a number of base b. Okay, so base b, here the concept of base comes. Base means the number of digits available in a number system. Let me repeat myself again. The base means the number of digits available in a number system. For example, binary number system consists of 0 and 1. That means 2 digits. So it is called a base 2 number system. In decimal number there are total 10 digits that are used, that is 0 1 2 3 4 5 6 7 8 9. So it is a 10 base number system. In hexadecimal we have 16 digits, 0 1 2 3 4 5 6 7 8 9 and a b c d e f. So there are total 16. So hexadecimal is a 16 based number. So here we can see the process of a decimal number converted to a base b containing number. So this is actually a generalized algorithm that if you provide it with a decimal number and provide a base b, it can convert it into any other based numbers. So let us get started in this algorithm. That first we say that in d variable we will keep the decimal number that needs to be converted. In b we will change the base of the number to convert it to, and s will be an empty string. Then here's a loop that while d is greater than 0 we will store the value of d modulus b in q, and in d we will store d by b, and we will append the value of corresponding symbol here with q in s, and then we will reverse and print s. So what does it does? We will try to see it through an example. So here is an example where we say that the decimal will be converted to a number of base 2. 2 means binary, so binary, usually 2 is a binary number system. So here we are keeping the value of b2, and I want to convert the number 19 into a binary number. So this is my objective. So let us get started. At first we will start the loop. Okay, now let's see. D is 19, so d is greater than 0 is true. Then we have q, which will keep the value of d mod b. Now we know the modulus operator actually keeps the remainder. So if we divide 19 by 2, as 19 is an odd number, it is essential that q will hold the value 1. If q is 1, then we will have an integer division of d by b. So if we divide 19 by 2 in integer division, we get 9. So d will store 9 over here, and thus in s I have written s plus corresponding symbol of q. Why am I writing this corresponding symbol? I will explain it in the next example. So corresponding symbol of q over here, it will remain 1 itself, so s becomes 1. Now you see this is a loop, so it will not end, it will go again up here, and as you can see d is currently 9, so d is greater than 0 is actually true, so we will once again hit the loop. So what happens next is, right now in d was 9, so when we divide 9 by 2, the modulus operator will return 1 once again, and over here d will be divided and d will contain 4, and as q was 1, the corresponding symbol will be added again, and as it is a string, it will concatenate with the existing part, hence s will become 1 1. Be sure to understand what's going on. If you are having confusion, pause the video and go up down a little to understand what's going on. Next up is, as you know, in previous one we had d equals to 4. So now once again the loop enters, but now 4 by 2 is actually gives the remainder of 0, so q will be 0 and d will be divided, so it will get 2. Now the corresponding symbol of q is 0, so 1 1 will be added with a 0, and this is the new string. However, d is still not 0, so we will go once again and we will have q equals 0, d equals 1, and s will append another 0. As you can see, d is still 1, so the loop will continue another time. Now this time q will be 1, d will be 0, and s will be this string 1 1 0 0 1. Now d has become 0, so the while loop will break, and the while loop will break, so s will be reversed and it will be printed. So if we see, it was 1 1 0 0 1, and hence it will be reversed to 1 0 0 1 1. And if you calculate, you will find that this is actually the binary representation of the decimal number 19. Now let us look at a different example. Now we want to convert our decimal number to a base 16, a hexadecimal number. So now the base is 16 and the decimal number will be, we are working with, is 26. Once again there's an empty string, and here we go again. First of all, we have 26, which will be divided by 16, and hence d modulus b, 26 modulus 16 will return 10. And when we see d equals to d by b, 26 by 16, it will essentially return 1. Now here comes the job of the corresponding symbol. You see, the value of q we found is 10, but we know that in hexadecimal after 9 it comes a. So corresponding symbol function will do what? When we pass it the value, it will turn it to a its corresponding actual symbol in a digit, and it will add it to it, so we will get a. And right now we can see that d is still 1, so the loop once again will run, and we will get the new values, which will essentially mean that s will become a1. And when we reverse it, we will get 1a. And if you check, you will find out that the hexadecimal representation of 26 is actually none other than 1a. Now you can pause the video, take your time, understand, but through this example I have actually explained that given any base number, okay, not only base 16 but base 2, given any base number, you can actually find the corresponding representation of that number of a decimal number. This is the algorithm. How about we reverse the process? Now we give a number of base b to decimal. We are given a number, we are given the base it's in, we want to convert it to a decimal number. You can also do that as well. At first we will need n, the base b number, b, the base of number to convert from. We will have s 0 and I is also 0. Now while n is not empty, we will take the last digit of n and store it in q. We will convert it to the corresponding symbol function, which will essentially convert it into a number. I mean, it will opposite, for example, the previous example, which I will explain later on over here as well. And then we will remove the last digit, append to the existing number, and we will increase the value of I by 1. So once again, I think it's better to show some examples. So here I have given a base 2 number. Once again, this is 10011, b will be 2, s 0 and I 0. Now let's start. N is not empty, q will be the last digit of n. What is the last digit of n? Let's start with that. N is starting off as 10011, so the last digit of n over here is 1. Q will have 1. In the next line, q will have 1 into 2 to the power 0, because I started off as 0. Right now I is 0, so 1 into 2 to the power 1 equals to 1. Next we remove the last digit from n, so it becomes 1001, and in s we add s with q. Q is currently 1, so s and q added to 1, I will be increased by 1, so I becomes 1. Okay, n is currently not empty, so the loop will continue. Here comes the next loop, 1001. Once again the last digit of n is 1, so q will be 1. But right now, as I is 1, 2 to the power 1 will be multiplied with 1, and we will get 2. The last digit of n will be dismissed, 1 will be gone, it will be 100. S now contained 1, now it will add 2, so it will become 3, and I's values will increase by 1. Once again another digit disappears from n, but now the last digit is 0, which will be multiplied by 2 square, which will eventually result in 0. N will become 10 by removing the last digit. S will become 3 because 3 plus 0 is 3, and I will be increased by 1. Thus another loop continues. Take your time, understand the process is actually same, and thus it goes on until finally, as you can see in this loop, n was 1, and so the new n is empty. So we currently have s equals to 19 and I equals to 5, but n becomes empty, so the loop breaks and prints s. So essentially the decimal representation of the base 2 format 10011 is s equals to 19. And in similar terms we can do the part of the hexadecimal as well. Now we have seen working with the decimal, but what about binary and hexadecimal and vice versa? So in this case we will use, remember that 2 to the power 4 is 16, so 2 is the base of binary number and 16 is the base of hexadecimal number. Well, one thing you can do, you can convert a given base to decimal and then convert it to the another one, that is the base. That is one option. If you do not understand, suppose you are given a number in binary and you are told to convert it to hexadecimal, you can first convert the binary number to decimal, then convert the decimal number to hexa. This is one procedure. Another procedure is using 4 bits of binary to convert it to a hexadecimal. There are multiple ways. You can surf the internet and use any of the valid systems. It's not very strict on my side that you have to do it like this. I will not do that. You are free to use your flexible options. Now, representation of numbers, I will just touch it a little bit. We will not complete it in this class. So when representing a number, it is very important to get the concept of words. Okay, we know bits and bytes, but in computer architecture or design or manufacture, they define something called a word length. They define that how many bits they will use to provide data for a single character or such stuffs like that. So what's the number of bits, and it is heavily dependent on the system architecture of the system you are using. That's written over here, what says varies from machine to machine. Computer process use binary, humans easily understand decimal, hexadecimal expresses more in less digit. So here are the 3 number systems that we use, and here is the concept of words, which will be later you will learn about them in brief in later courses. Okay, so this is another thing that we have all learned a little in our previous courses, which is representation of integer numbers. Now, if we are given a word size of n, the maximum possible number is 2 to the power n minus 1. That is, if I want to express a word using n bits, the maximum possible number that is possible to be expressed using n bits is 2 to the power n minus 1. And negative numbers are stored as 2's complements. 1's complement, there is 2's complement, and it's stored as 2's complement. So this is how integer numbers are stored in a computer. Now here comes the floating point representation. I will not put too much pressure on how to do. We will discuss it once again in later class. Just remember that floating point representation has multiple standards. I will be showing only one standard in class. You can surf the internet for better understanding, and you can choose any one standard you want to use, but they are essentially very close and very same. So at least in all representations there is one there are few topics common, that is floating point representation requires you to save numbers in exponent forms, where we use f and capital E. F is called a mantissa and E is called an exponent, and the entire memory location is divided into 3 parts. So I think I will stop the class over here for today's session. We will start from this part in the next class, inshallah. Thank you everyone. See you next time. Assalamu alaikum.